IPCC and relationships to biophysical economics and climate change policy, perhaps. So, Albert,
I do.
take it away. Thanks.
So I did the caffeine this morning, and I actually have to go pretty quickly through this, but I have the longer 8,000 word paper if anybody wants the references and is looking at various stuff. I only have a limited number of copies, but happy to, somebody has the key code card for the copier upstairs, I can make more.
Good title. Good title.
All right, well, I was kind of hoping Dennis Meadows would go ahead and do all the latest climate science ahead of time because I left all that part out. Dennis, if you're watching, we miss you, buddy. Come next year. Anyway, so on to Paris. We were gathered in 2015, and the IPCC had warned the delegates in fairly clear terms that there was a finite cap of cumulative carbon dioxide emissions, no more than 1,200 gigatons or 327 gigatons of carbon from 2015 onwards to stabilize climate below an average of 2 degrees Celsius above pre-industrial conditions by 2100, and that only had a likelihood of 66%. Well, you know, the 2 degrees is a longer discussion, and I go into it in the paper. It was a political decision back in 1996. It was adopted by a number of government bodies, and so it sort of carried its own inertia. But there was a lot of concern within the conference about whether that was adequate. From my view, I think the quota is fiction, that we're already past the point at which 2 degrees is baked in the cake. Who am I to argue with consensus? The cap corresponds to about 30 years of current emissions levels of 37 gigatons carbon per year, carbon dioxide. So it's thought by most delegates that it would be a matter of spreading gradual decline in emissions over the course of a few decades. However, during the past decade, we can look at emissions from fossil fuel combustion and see that it's continuing to increase. Production increased 65% above the 1995 level. So the IPCC's Working Group 3 considered in the 5th assessment report over 1,000 emission pathways, and we have to top out at 430 to 480 parts per million CO2, but we won't. To return to 2 degrees, we're going to not just stop emissions, we're going to have to require global net negative emissions in the second half of the century. So we're going to go past, and we have to go back. Reports have identified, this is the NASA current view of climate temperature anomalies going back to 1880. On the upper end of the chart is the 1.5 limit. We'll probably cross that in a couple of years. 2040, we'll see 2 degrees, somewhere around there, give or take. This is meteorological station data. This is not projection. So because of the inertia of coupled systems, these changes are very unlikely to be preventable. If every country meets its pledge for nationally determined contributions, an approximate 3.4 degrees of global mean warming is expected by 2100. If you follow that meteorological data chart out, even meeting all of the targets that are currently pledged, 3.4 is the likely outcome by the end of the century. This estimate should be regarded as tentative because there are many tipping elements like ice melt at the poles, permafrost, clathrate decomposition, albedo increase from desertification, and those all create positive forcings and feedbacks, not all of which are fully modeled. Various tipping elements are arrayed such that 3 degrees tips into 4 degrees, 4 degrees into 5 degrees, and so on, until a new equilibrium is reached at some point. That equilibrium could be at 7 degrees, it could be at 12 degrees, we don't really know. So despite these uncertainties, it's often assumed that humans will be able to adapt to any possible warming However, as mammals, whose internal body temperature is regulated by sweat glands, the physics of skin moisture evaporation and biology of heat stress impose a robust upper limit to adaptation. Going over 35 degrees C for extended periods would induce hyperthermia in humans and other mammals as dissipation of metabolic heat becomes impossible. This would begin to occur with a global mean warming of about 7 degrees, calling even the present habitability of some regions into question. Even with only a few degrees of warming, regions of intolerable temperature could spread to touch many more parts of the human population. Given the overall decline of net available energy in the coming decades, it seems unlikely that air conditioning would be able to keep up. At present rates of emissions, by 2020, there will be a 1,000 gigaton budget left, or 10 gigatons per year, provided at the time of Paris. So, from the time of Paris forward, we're looking at already having used up 200 of a 1,200 gigaton budget. There's only a limited time to bend the curve from upward to downward before self-reinforcing tipping points take the situation behind our control. Assuming we have not already passed that threshold, the longer we delay, the steeper the pitch must be on the descent. And from where we stand now in 2018, to have a realistic chance of averting disaster, we need to reach 11% decline rate per annum from 2036 or better, a 20% decline slope in 2037. According to the IPCC calculations, the 11% slope would get us to 2 degrees at the end of the century, and the 20% decline slope would get us to 1.5. Well, people in this room are familiar with the exponential function. 11% decline slope is the inverse of doubling your fossil economy every 7 years. So halving every 7 years. Try to imagine half the numbers of commercial passenger flights in 2025 as today, or half the numbers of gasoline-powered engines, half the number of Walmart superstores bringing full cargo ships from Shenzhen to Houston, and then have that again by 2032, and again by 2039. You get the picture. We've been hearing more about renewables in this conference, but avoided emissions will not be adequate. Even replacing fossil fuels with sunlight, wind, and firewood will not bring carbon back into the safety zone fast enough. These are charts from the SSP database on renewables, and they will not bend the curve downward for fossil fuels. In most scenarios, renewables will only help fill the growth gap in overall supply increases, which is all we've done so far. On the left, in colored bands, are the papers on negative emissions technologies appearing in peer-reviewed literature prior to Paris. Each color represents a separate IPCC review period, so AR1, AR2, AR3, AR4, AR5. And to indicate how much this research has accelerated, just the number of published journal articles on biochar alone in the first 3 months of this year was more than all the negative emissions technologies papers in the previous 25 years between 1990 and 2015. The charts to the right compare tech readiness, side effects, and permanence for 5 different categories of negative emissions technologies, and I'll touch on a few of these. To have any chance of averting catastrophe, drawdown has to be ramped up quickly to 4 gigatons carbon dioxide per year by 2040, 10 degrees carbon dioxide per year gigatons, 10 gigatons by 2050. So there are 5 generally recognized categories of carbon dioxide removal that in some combination could achieve this, and this is the major study finding that I'm reporting here. And I actually get into this in some detail in a book coming out this September from Chelsea Green, which I'm shamelessly promoting right now, called Carbon Cascades by Kathleen Draper and myself. Applying the biophysical economics analysis, we conclude that it would be possible to economically scale all of these techniques to achieve drawdown, which is net sequestration over emissions, by mid-century if fossil emissions reductions were also forthcoming. We also find that such a response would require unprecedentedly rapid social change in the way that human habitation relates to the environment. In the run-up to this meeting, some new papers were published that revised our initial conclusion. So if you're going on our abstract that was circulated before the meeting, we've revised our findings, particularly with respect to direct air capture. So the new paper has better findings. If we look at the cost-optimal scenarios without delays or constraints in technology deployment, you can project that emissions could be made to peak around 2020, followed by rapid reductions, carbon neutrality sometime in the second half of the century, and eventually net carbon dioxide drawdown from the atmosphere. In UN policy development, this has sometimes been referred to as the default strategy. Some investigators suggest that these targets could be achieved entirely by enhancements to natural sinks. This shows afforestation and reforestation meeting the criteria of no farmland or parkland conversion, no food versus fuel controversy, respecting smallholders and indigenous peoples, attention to albedo, suitable soil types, and so forth. Many negative emissions technologies under discussion necessarily lack proof of efficacy at scale. The sole exception to this uncertainty is afforestation and reforestation, because we have historical examples where significant carbon was successfully withdrawn from the atmosphere by human activity, resulting in global climate response and regional cooling. Population decreases during historic events such as the Black Death in Europe in the 14th century, the Mongol invasion of China and Eastern Europe in the 13th and 14th century, the fall of the Ming Dynasty in the 17th century, and the conquest of the Americas in the 16th and 17th centuries, brought about the abandonment of agricultural land, allowing forests to regrow and remove CO2 from the atmosphere. The Mongol invasion dropped atmospheric carbon dioxide by 700 million tons. The Columbian encounter reduced atmospheric carbon dioxide by 10 gigatons, contributing to Europe's Little Ice Age. The amount of suitable and readily available mineral silicates, it far exceed the requirements for sequestering all conceivable anthropogenic carbon dioxide emissions. However, these techniques require mining, grinding, transport, and dispersal with energy and environmental demands. Another technique is in situ carbonization, injecting carbon dioxide into silicate rock. At the end of 2017, a facility in Iceland began operations using geothermal power to capture CO2, flush the filters into water, and pump it underground. And there the CO2 reacts with basaltic bedrock to form solid calcium carbonate, limestone, after about 2 years. At full operational scale, that system is expected to capture 50 metric tons of CO2 annually. The cost is in excess of $10 million. 50 tons is about the same output of a single U.S. household in 1 year. The cost of each ton, even amortized over a century, will run into thousands of dollars, and needless to say, there are a limited number of places on Earth where such a scheme would even work. Yet there is a way that mineralization could be sustained at scale. Rock weathering is a major source of most plant nutrients. Depending on the degree to which soils have lost nutrients from leaching and crop export, it is economically beneficial for farmers and herders to amend soils with rock powders that slowly release natural minerals for decades. These can provide all the nutrient elements plants need, except for nitrogen, and make them directly available to plant root mycorrhizae. Mixed with biochar to retain nutrients and water, they become slow time-release fertilizers. The requirement for a continuing supply of minerals to sustain soil fertility supplies a robust motive for smallholder farmers and ranchers to devote the energy to accomplish that strategy, even in the absence of a fossil economy. Direct air capture offers the possibility to capture carbon dioxide, but it's unlikely economic in the first generation of DAC installations, which employ amide sorbents to bind carbon dioxide from ambient air and concentrate from less than 1,000th of a percent, 410 parts per million, to greater than 95%, 950,000 parts per million. The amides are scrubbed to recover the substrate, a process requiring high temperatures, and the carbon dioxide is cooled and transported to storage, which are more processes demanding energy. Globally, less than a dozen small demonstrations have been done so far, and there are problems. To minimize transport costs, DACs can be sited close to carbon dioxide storage sites, but they still require significant energy and or heat to operate. Current costs of an AMI technology range from $200 to $1,000 per ton of carbon dioxide compared to $30 to $100 ton for capture from flue gas. And that difference relates primarily to the concentrations of your starting point. It has frequently been suggested that carbon dioxide could be discharged to the oceans by dissolving it in the mid-depth ocean of 1 to 3 kilometers, or by forming pools of CO2 at the sea bottom where the ocean is deeper than 3 kilometers and consequently CO2 is denser than seawater. These schemes neglect the negative effect of ocean acidification as that technology scales. Geologic storage is also beset with problems. If the release of fugitive methane from hydrofracking is any indication, the rate of CO2 leakage after geological injection could be from 10 to 30% per year. So what are they doing now? Now there's some limited agricultural and industrial applications for pressurized high purity CO2, but many of these depend themselves upon an industrial economic infrastructure that will be compromised by the phase out of fossil energy. At the current stage of commercial development, operators have been selling harvested CO2 instead of storing it. This is catch and release to the atmosphere rather than drawdown. Until the storage problem can be shown to have commercially viable anti-fragile path to developments, amide recycling DAC is unlikely to provide a business model, business case. However, recent advances in DAC research do give hope. And this is one of the places our paper changed in the last few weeks, particularly since the conference that was held in Stockholm last week on negative emissions technologies. Work by Klaus Lackner, for instance, is producing low concentration 2% carbon dioxide and feeding that to tanks of algae for production of food, fiber, medicines, biogas, and chemicals. That makes a business case. Algal DAC meets the requirements of ecosystemic, benign, low-cost, socially acceptable technology with adequate incentives to function in the absence of the petroleum economy. Algal DAC is flexible enough to run on most types of renewable energy, including its own biogas. It could supply algae biogas to a BECCS system. It could be adapted to extract CO2 from seawater using membranes. Anaerobic digestion of cellulosic waste and with biosolids with microalgal absorption of carbon provides a favorable return on investment in both energy and financial terms without the problem of leakage, although unless converted to biochar, the withdrawal is still temporary because the carbon remains in labile form and will return to the carbon cycle either as food or fuel. Combining anaerobic digestion, algal, DAC, BECCS, and biochar could provide a total solution. So now we get to BECCS. This is the favorite of the IPCC. A lot of AR7 is going to be devoted to this. Carbon capture and storage, CCS, in its earliest formation was coal scrubber technology coupled with geologic and marine storage of carbon. Capturing carbon dioxide in flue gas added only incrementally to power production costs, but storage has proven quite expensive and unreliable. Two newer types of CCS, bioenergy with carbon capture and storage, or BECCS, and pyrolysis bioenergy with carbon capture and storage, or PYCCS, are undergoing development. The IPCC projection was that BECCS would have between 5 and 50% of primary energy supply for carbon dioxide to be held below 780 ppm in 2100. BECCS has come under scrutiny for its need for large land areas on which the biomass would be cultivated. There's concern that that could interfere with food security or safeguarding terrestrial ecosystems. However, in the move away from fossil energy, bioenergy deployment is likely to be as high without BECCS as it is with BECCS. In some scenarios, bioenergy upscaling is even more rapid. This is because bioenergy is a versatile technology that has applications across a range of energy needs. While large-scale DAC and BECCS are intended to lower the pressure on climate change, they could steer the Earth system closer to the boundaries for fresh water use and lead to further transgression of the boundaries for land system change, biosphere integrity, and biogeochemical flows. Similarly, large-scale afforestation and reforestation could affect Earth's albedo, the amount of sunlight energy radiating into space, and also the water and nitrogen cycles that supply significant greenhouse gas. Some people may be familiar with some people may be familiar with this image on the left, which is from Dominic Wolf and Johannes Lehmann and Jim Amonette at Cornell. It was published in Nature in 2010. It summarized inputs, process outputs, applications, and impacts of BECCS if augmented with biochar production. I'm going to skip their summary of it, but essentially it shows the removal of CO2 by photosynthesis enhanced by biochar amendments and going back to the soil for various other benefits. Earlier this year, Kathleen Draper and I submitted for publication our book on this subject, Carbon Cascades, and we then proceeded to elaborate upon the Wolf diagram, drawing upon some of those 11,000 papers on biochar last year, adding recent developments in pyrrolysate sources and sinks. So for instance, we could calculate how much photosynthetic carbon could replace not only fossil source carbon, but other common materials in modern life, such as chemicals, aggregates in concrete, polymers, asphalt, clay, sand, and more. And with this new perspective, a world of opportunity opens in terms of how and to what degree biochar can displace materials that either have a large carbon footprint, are non-renewable, are toxic, or are simply too expensive. By carbonizing underutilized waste streams and customizing production facilities, biochar can help individuals, companies, and nations to meet their decarbonization targets. And unlike some of the other negative emissions technologies, these biorefineries also tick the many boxes of the UN Sustainable Development Goals. They can be village scale. They can form the basis for an eco-village or a bioregional economy. Since pretty much all the waste can be pyrolyzed and reused, this can form the basis of a new circular economy. In conclusion, we believe that because of acidic inertia, it's unlikely emissions will peak around 2020, or that negative emissions technologies will be deployed rapidly. That said, it is technologically possible to redeem the atmosphere to its pre-industrial condition by following the specifications that I've been giving. By going small, keeping it modular, keeping it local, looking at the fragility of the system, and working ecosystemically. While actions by governments in support of these initiatives is important, it's our conclusion that the initiative must come from the bottom up. We suggest this can only be accomplished by incentives such as meeting basic needs and the profit motive. The principal impediment is not human technological prowess. The impediment is cultural inertia, which is to a significant extent biologically determined. An example of what's possible is being provided in a small experiment presently underway in the Dominican Republic. In a small-scale biorefinery, its originators call a cool lab. Normal crop residues, including those from tropical agroforestry and so-called supergrasses, are processed first by chemical nutrient extraction, then by pyrolysis to produce electricity, biochar, and the numerous products that biochar offers, such as animal feed supplements, cathodes for fuel cells, water filters, and aerogels. In the first year of operation, the return on investment was greater than 50%, meaning that the lab pays for itself in the first 2 years of operation. And this occurred during the same growing season as they sustained nearly direct hits from hurricanes Irma and Maria. Is it possible to unscrew the pooch? Yes, the impediments are cultural, not technical. That said, there is no avoiding a very significant redesign of our global civilization. In a very short time, it requires a shift of global industrial economies no less profound than that which transformed Western and Soviet manufacturing in 1940. For the owners of factories, steel mills, mines, and myriad enterprises, a paradigm shift would have to transform their holdings from carbon polluting to carbon trapping almost overnight. In 1940, entire industrial economies switched instantly from producing consumer goods to providing war materials. It was a rational response to a visceral threat. So children, go forward and invent something. Hopefully it will not have unintended consequences of fossil fuels. Just a last minute plug, I do have a book that talks more about the Paris Agreement, how it came into being, called the Paris Agreement, and another one called the Biochar Solution from 2009, with the sequel coming up in Carbon Cascades. Thank you.
Thank you. on good time, so we have a good time for questions for 5 minutes.